Hello everyone, in this presentation we are going to discuss about tasks and data. So each task has its own private context which includes the register values, a program counter and a stack. However, all other data, that is global variable, static variable, initialized, uninitialized and everything else is shared among all of the tasks in the system. As shown in the figure 6.5, task 1, task 2 and task 3 can access any of the data in the system. So the task typically has its own private data structure which are not available to any of the tasks. So here you can see in this diagram. So the real-time operating system has own real-time operating system data structures which is separately private, and task 1 has its own separate task 1 registers and task 1 stack. Task 2 has its own separate registers and it has its own separate stack. Task 3 has its own separate registers and it has its own separate stack, and all other global variables are available here. Okay, so task 1 registers, task 2 registers and task 3 registers, right? These registers are dedicated for tasks which helps in context switching, which reduces the return time from the interrupt service routine. That is what we are going to discuss here in this particular thing. Okay, so what is context? It's very important. What is context? Each task has its own private context which includes the register values, program counter and a stack, as we discussed here. The RTAS has its own private data structures, register banks and stack memory, which are not available in any of the tasks as shown in the figure 6.5. Okay. Here if we see, there is sharing data among real-time operating system tasks. So say for example we are looking at underground tank monitoring system. So there is a structure which is written as tank level and its corresponding time, which is one structure. There is a button task which responds to the button, which is highest priority, and there is a level task which calculate the tank level, and switching between the task will happen automatically whenever the highest priority task unblocks. That is what. So it is something like underground tank monitoring system as we discussed. Here you can see this button task is the highest priority task. So this will block under, it will block until the user pushes a button, and if the user presses the button, then the corresponding tank data will get computed and then it will display to the user. Okay, so this is the computation task, so which is lowest priority task. So the tank level is getting computed here in this particular function. Okay, so coming to the shared data problem. So already we have discussed about this shared data problem clearly with some examples. So similarly here in the Simon book, the shared data problem is explained with some B count errors. That means there is an error task which keep on putting the value in the errors. So Simon author has explained clearly with the error task and how it gets updated. So this is the C program that what we have written, and whenever the interrupt comes here, and there is a possibilities of error. Why? Because the single C program may have several assembly language program, and if the interrupt happens in between the assembly language program, there is a possibilities of shared data problem. That was explained very clearly, as like how we have discussed about shared data problem in the 8051 code. Okay, so this is something like shared data problem, and here there is one interesting thing we have to concentrate: atomic function. What is atomic function? Okay, so this is very interesting. The part of the program which is said to be atomic if it cannot be interrupted. A part of the program is said to be atomic if it cannot be interrupted. That means the more precise way to look at the shared data problem is that it is the problem that arises when the interrupt routine and the task code shares the data, and the task code uses the share data in a way that it is not atomic. It's very interesting, right? So the part of the program is said to be atomic if it cannot be interrupted. Okay. So the very clearly the option B shows very clearly the more precise way to look at the share data problem is that it is the problem that arises when the interrupt routine and the task code share data, and the task code uses the share data in a way that it is not atomic. When the task code is atomic means it cannot be interrupted. How to make the task code as atomic? By disabling it. That's all. So when we disable the interrupts around the lines of the task code that use share data, we have made that collection of lines atomic, and we have therefore solved the share data problem. That is what we have experimented. It is what we have demonstrated in the IT51 simulation code, how to make that particular code as atomic. Okay. So what do you mean by atomic function? A part of the program should be atomic if it cannot be interrupted. It's very interesting. So what do you mean by reentrant function? This is another interesting question. Reentrant functions are the functions that can be called by more than one task, and that will always work correctly even if the RTAS switches from one task to another in the middle of executing the function. This is very interesting, right? Atomic means which cannot be interrupted, but reentrant function means are those functions which can be called by more than one task, and that will always work correctly even if the RTAS switches from one task to the another in the middle of executing the function. It's very interesting, right? So two functions, right? Atomic function and reentrant function, which we need to remember when we talk about operating systems. Okay. So what are the three rules that to decide a function is reentrant or not? Okay, we have to confirm that whether the function is reentrant or not means we have three rules need to be focused. The reentrant function may not use any variables in a non-atomic way unless they are stored on a stack of the task that called the function, or otherwise the private variables of the task. Reentrant function may not call any other functions that are not themselves reentrant. The reentrant function may not use the hardware in a non-atomic way. So the reentrant functions more or less it should be atomic, then only it can be a reentrant function. Even though the task code and the interrupt service routine shares the data, the shared data problem will not happen. Okay. So there is something like semaphores, which is very important feature in the real-time operating system, which we are going to discuss it now. Okay. How to prevent share data problem using real-time operating system? So disabling interrupt is the only way with respect to our conventional C programming for our 8050 microcontroller. That is what we have experienced it. But when we are using real-time operating system, how to prevent the share data problem means share data problem is prevented using semaphores in the real-time operating system. Okay. So how to prevent share data problem using RTAS? RTAS has a tool to deal with the share data problem. That tool is a semaphore. So what is semaphore? Semaphore is not the word which is coined for a real-time operating system. Something like port is a place where exchange of goods takes place between two different medium. That's why the same name comes to the parallel port and serial port, where the exchange of data happens between the external world and internal world. Here also semaphore is mainly related with the trains. So we'll see that. So according to the author, Simon author, here you can see there are this is called semaphore, right? So normally we used to say kaikati, semaphore. Okay. Semaphores will prevent the collision of the trains. Semaphores will prevent the collision of the train. So let us say there is a black train which is traveling in the track. So these are all the semaphore signals. This is the signal to the particular trains. Here if you see, when the train is coming, right? When the train is coming in this way, whenever the train crosses this signal will close this. That it will stop. It will stop the following train. Whenever this train, the first train crosses this particular signal, it will open this particular signal and then it will close this particular signal. Say for example, when this train is moving here, if the second train comes here, the second train comes, this will never allow the second train to collide over the first train, because the signal is blocked. Signal is blocked, say for example. So let us say this is the goods train and this is the express train. Express train will come fast and hit the goods. So to prevent the collision, right, of the express train with the goods train, this semaphore signaling will be helpful, right? So this signal will close until this train, goods train, crosses this particular signal. When this goods train crosses this particular signal, as you see here, this signal will get closed. So this opened signal will get closed, and this signal will open. That is, this semaphore will open and allow this train. So even though it is an express, it will come quick until it will come and stop here. Why? Because this signal is closed. And similarly, this goods train, if it crosses the next signal, that will close and this will open. So this is semaphore signaling, which was used in earlier days. Nowadays we are using LED signaling and so many other advanced methods. Earlier, this kind of semaphores, which will prevent the collision of one train and another, the same concept is used here in the real-time operating system to prevent the shared data problem. Okay, so that is what we have to understand here. So let us see what the author says. Trains do two things with semaphores. First, when a train leaves the protected section of the track. When a train leaves the protected section of the track, it raises the semaphore. Look at the third row of figure 6.11. Okay, third row. First train which leaves the protected section and raises the semaphore to the second train. Okay, so in the figure 6.11, this third row, the first train leaves the protected. This is the protected section. It leaves the protected section and raises the semaphore to the second train. Okay, so when it leaves the protected section, it raises the semaphore, so the second train can come over here. That's what it's mentioned here. Okay, so that is what. Then second, when a train comes to a semaphore, it waits for the semaphore to rise. When the train comes to the semaphore, here you can see when the train comes to the semaphore, it waits for the semaphore to rise. Look at the second row of the figure 6.11. Second train waits for the semaphore to rise. Here, the train comes, it waits for the semaphore to rise here, as you see in the second row. If necessary, passes through the semaphore and lowers the semaphore. Look at the second row of the second train, waits for semaphore to rise. Typical semaphore in an RTAS works much the same way. Okay, that's why it's very simple. This is the protected region. Whenever the first train crosses this protection region, then only it will opens the semaphore. When this train crosses the next protected region, then only it will open the semaphore and it goes on. So semaphore is a signaling device which prevents the collision of the train. That is understood very clearly with this example, right? And there are different types of semaphores. Here you can say there is something like binary semaphore. How it works. So what is binary semaphore and how it works? Binary semaphore is much similar to the railroad semaphore. The typical RTAS binary semaphore works like this. Task can call two RTAS functions. A task can call two RTAS functions. One function is take semaphore function, another function is release semaphore function. How we can relate here is, take semaphore is something like disabling interrupt, and release semaphore is something like re-enabling the interrupts. What we did in the shared data problem with respect to the conventional C programming with respect to 8051. So take semaphore is something like disabling interrupt, and release semaphore is something like enabling interrupt. Okay, so take semaphore and the release semaphore are the two functions of the real-time operating system, which has to be used in the critical section where we predict or where we expect the shared data problem may happen. That is the one we need to understand. So if one task has called the take semaphore to take the semaphore and not called the release semaphore to release it, then any other task that calls take semaphore will block until the first task calls the release semaphore. Because if lowest priority task take the semaphore, the highest priority task will also try to take the semaphore, but there is no semaphore means the highest priority task, even though it is highest priority, will never go to the execution state. It will come back to the blocker state until the semaphore is released from the lowest priority task. That is the one we need to understand. So only one task can have a semaphore at a time. So until the lowest priority task releases the semaphore, safely it can complete all the execution and preventing the shared data problem. And once if it completes the execution, that means once it comes out from the critical section, it leaves the semaphore, then highest priority task will take the semaphore and then it will start executing comfortably. Okay, so this semaphore is used to prevent the shared data problem, as we know very well. Okay, this is binary semaphore, which is most widely used for one particular shared data problem analysis. And there are multiple semaphores. Okay, so what is the significance of multiple semaphore? The example that what we have discussed is underground tank monitoring system. In the underground tank monitoring system, there are two temperature sensors. When the two temperature sensor values are not equal, it has to switch on the fire alarm. That is the one we have discussed, right? So there is a possibility of shared data problem in the temperatures. Why? Because this temperature data is shared between the read temperature task as well as computer temperature task. So for the temperature, we are using Semaphore, say for example. And there is some other two tasks similar to the temperature task where we have to concentrate on the pressure. Okay, so if the pressure values, pressure variables, pressure 1 and pressure 2 variables are shared between the some interrupt service routine and the some tasks, and if there is only one semaphore, if the temperature task takes the semaphore, means the pressure task should also will wait for the same semaphore, which will delay the process. Okay, so hope you understand. So for the temperature, we can use one semaphore, say for example semaphore A, and for pressures we can use semaphore B. So for temperature tasks, they can use semaphore A, and pressure tasks can use the semaphore B, where there is a need for multiple semaphores to speed up the process. Because if there is only one semaphore, all task has to wait whether it is sharing the data or not for that semaphore, because if you have multiple semaphores for a particular variables, and it will be comfortable for us to speed up the process, where the other task need not wait for the same semaphore. Hope you understood. Since most of the RTAS allow us to have many semaphores, as we like, each call to the RTAS must identify the semaphore on which to operate. If one task takes the semaphore A, another task can take the semaphore B without blocking. Similarly, if one task is waiting for semaphore C, that task still will be blocked even if some other task releases semaphore D. It's very clear, you understood, right? So temperatures needs semaphore A, pressure needs semaphore B. Temperature tasks uses semaphore A to prevent the shared data problem with respect to the temperature. Pressure tasks can use the semaphore B to prevent the shared data problem with respect to the pressures, and both are isolated, both are separate, and both can work independently, and it can protect the system from the shared data problem through semaphores. What is the advantage of having multiple semaphores? It's very interesting. That is what we have discussed now. Let us see in the author's point of view. So whenever a task takes a semaphore, it is potentially slowing the response of any other task that needs the semaphore, same semaphore. In a system with only one semaphore, if the lowest priority task takes the semaphore to change the data in a shared array of temperatures, the highest priority task might block waiting for that semaphore, even if the highest priority task wants to modify some errors and couldn't care about the temperature. So modifying the error is one task, modifying the count of the errors, and modifying the count of error task has nothing to do with the temperature, but unnecessary it has to wait. That's what the message says. So by having one semaphore to protect the temperatures and a different semaphore to protect the error count, we can build our system so that highest priority task can modify the error count even if the lowest priority task has taken the semaphore protecting the temperatures. So different semaphores can correspond to different shared resources. That's what we need to understand. How does RTAS know which semaphore protects which data? RTAS do not know which semaphore protects which data. It doesn't. If we are using the multiple semaphore, it is up to us to remember which semaphore corresponding to which data. The task that is modifying the error count must take the corresponding semaphore. We must decide what shared data each of our semaphore protects. That's very important. How semaphore act as a signaling device? It's very interesting, right? How semaphore is used as a signaling device? Suppose the task that formats printed reports, building those reports into a fixed memory buffer. Printer interrupts after each line, and that the printer interrupts routine feeds the next line to the printer each time it interrupts. In such a system, after formatting one report into the fixed buffer, task must wait until the interrupt routine has finished the printing that report before it can format the next report. One way to accomplish this is fairly easy: to have a task wait for the semaphore after it has formatted each report. The interrupt routine signals the task. When the task gets the semaphore and unblocks, it knows that it can format the next report. It's very interesting to discuss. So using Semaphore is a convenience, it is an advantage, but there are several problems associated with Semaphore. Let us see one by one. What is the problems in using Semaphores? So the reading shows that the Semaphore tool is in our task is one of the solution to overcome the shared data problem. This is not true. Our systems will probably work better the fewer times we have to use Semaphores. Problem is that Semaphores will work only if you use them perfectly, and there are no guarantees that it will we do that. Okay, so what are the problems associated with Semaphores? When we forget to take the semaphore, okay, even though Semaphore features are available, if we forget to take the semaphore, then there is a possibility of shared data problem. Okay, Semaphore will work only if every task that accesses the shared data for read or write uses the semaphore. If anybody forgets, then our task may switch away from the code that forget to take the semaphore and cause the ugly shared data bug. So forgetting to take the semaphore will create a problem, and forgetting to release the semaphore is again a big disaster. If any task fails to release the semaphore, then every other task that ever uses the semaphore will sooner or later block waiting to the task, waiting to take that semaphore, and will be blocked forever. Okay, so if any task fail to release the semaphore means that the other task which is in need of semaphore will be blocked forever, which is again a big disaster, as we know very well, right? So taking the wrong semaphore, if we are using multiple semaphores, then taking the wrong one is also as bad as forgetting to take the one, as we know very well. Okay, so holding the semaphore for too long, whenever one task takes the semaphore, every other task that subsequently waiting that semaphore has to wait until the semaphore is released. If one task take the semaphore and then holds it for too long, other task may miss the real-time deadlines. It's very important. So there are multiple problems beyond this, but at least these four things that we need to understand. Forgetting to take the semaphore is first problem. Forgetting to release the semaphore is the next problem. Taking the wrong semaphore is the third problem. Holding the semaphore for too long is the fourth problem, or the four major problems which will happen if you are not using the semaphore properly. Okay, and there are multiple semaphore variants, right? So there are a number of different kinds of semaphores. Here in an overview of some of the more common variants. There are counting semaphores, right? Some systems offer semaphores that can be taken multiple times. Essentially, such semaphores are integers. Taking them decrements the integer, and releasing them increments the integer. If a task tries to take the semaphore when the integer is equal to 0, then the task will block. It's very interesting, right? The task will block. So this will be another very interesting, right? Counting semaphores. Okay. Then resource semaphores. There is another kind of semaphore called resource semaphores. Some systems offer semaphores that can be released only the task that took them. These semaphores are useful for the shared data problem, but they cannot use it to communicate between the two tasks. So mutex semaphore. Some RTAS offers one kind of semaphore that will automatically deal with the priority inversion problem, which is mutex semaphore. Okay. So the different variants are counting semaphores, resource semaphores, and mutex semaphores. It's very interesting. So to summarize, before we summarize, we look at the Simon author book. So this is the shared data problem with respect to the Simon author book, and applying the Reentrant rules, and semaphores and shared data is being discussed here, and RTAS semaphores with respect to button task and level task is being showed as discussed, right? Here you can see take semaphore and release semaphore in the highest priority button task, and you can see take semaphore and release semaphore in the lowest priority level task, and this is the place where the shared data problem will happen. So this is the critical section. Wherever there is a critical section, semaphores are used something like take semaphore and release semaphore as told, right? Okay, so it is very clearly explained here in this diagram. So this is the tank level, calculate tank levels task, and this is the respond to button task. First, calculate tank level task takes the semaphore, as you see here, it takes the semaphore, and it updates the first tank data. Then tank data means what? Tank data temperature. First temperature is getting updated, and before updating the second temperature. That's very important. After updating the first temperature, before updating the second temperature, an interrupt comes. because the respond to button task is having highest priority, so it goes to the highest priority. When the user presses the button, the highest priority button task unblocks and RTAS switches this to the highest priority task. Here also if you see in this code, in the button task also, this is the button task. In button task also we are willing to take the semaphore, but the semaphore was already with the level task. So the button task, even though it is highest priority, it has nothing to do without semaphore. So it will try to take the semaphore. There is no semaphore because it was already taken by the lowest priority task. So the semaphore is not available. The button task blocks and the RTAS switches back. So again it switches back, it updates the second temperature, and then it releases the semaphore. Soon it releases the semaphore, it goes back and it completes all the particular activity, compare temperature or printing, something like that, and then it will release the semaphore and it blocks. Okay, so level task takes the semaphore, and even though the button task is highest priority task, it will try to take the semaphore, and because semaphore was already taken by the lowest priority task, even though it is highest priority, because there is no semaphore, button task has nothing to do, so hence it will go to the blocked state. After completing the updation of two temperatures in this critical section, calculating the tank level task releases the semaphore. So you are taking the semaphore and then you are releasing the semaphore. That's very important. Once if it is released, the highest priority task completes the task, and then that is also releasing the semaphore, and then this process continues. So this is how the real-time operating system uses the semaphores to prevent the shared data problem according to this author. So this initializing semaphore means this is the syntax with respect to the nuclear with respect to the corresponding real-time operating system. So priority, read, control, the nuclear reactor. So the nuclear reactor, how the temperature is being read, some example is being given, right? Okay. So pending means take semaphore, posting means release semaphore. There are different syntaxes, that's all. So OS means it is a syntax, right? Okay. So OS, these are all the RTAS functions, right? So as told, right, automatically the application program runs first, then only RTAS will run. Here only OS initialization is happening, the main routine only. Okay, so then only OS is starting, right? What do you mean by OS initialization? Our application program says that about the tasks. Okay, there is something like read temperature task, and there is something like control task, etc. And the priority of the task. Tasks are also having priority, you see. Task priority read, task priority control. What is task priority read? Task priority read is 11 and task priority control is 12. Okay, so those priorities, 11 priority, every task has a priority, that is also very clearly given, and every task has a stack. Okay, so read stack has 1 KB stack size and control stack has 1 KB stack size. So separate stack memory and separate priorities for each task as told in the RTAS, which is being understood now by looking at this figure 6.4. Okay, so in the void main you are initializing the operating system, and then we are informing the operating system about our particular application through the corresponding task and its corresponding priority and its stack size with the corresponding pointers as we see. Then we are starting the real-time operating system. Then real-time operating system will take care of all the task execution as 3 states, right? Ready, running and blocked state, etc. And here if you see OS pending is something like take semaphore, post is something like release semaphores, as we see here. In the read temperature task, the semaphores are being used to prevent the shared data problem, and because in this particular read temperature task with respect to nuclear reactor, the temperatures are getting updated. So this is the critical section where shared data problem may occur whenever the interrupt happens in between these two lines. So pending and posting are the take and release semaphore which prevents the shared data problem, and this is the control task which shares the same temperatures, compare temperature, right? If temperature is not equal to temperature 2, as like how we do the with 8051. So here also OS pending, OS post, take semaphore and release semaphore. So control task is another using take semaphore and release semaphore, where there is a possibility of shared data problem, and read temperature task is also using take semaphore and release semaphore, where there is a possibility of shared data problem. So this is the example that we have to understand. So reentrancy and semaphores, reentrant functions are the functions as discussed, right? And the same problem, take semaphore. There is something like nucleus real-time operating system. Nucleus real-time operating system has the syntax of OS. So it starts with OS, right? OS semaphore pend, OS semaphore post, OS semaphore pend, OS semaphore post, OS time delay, OS start, OS task create, OS task create. If initializes with OS, when it initializes OS means it is MuCOS, microcontroller operating system. This is one kind of real-time operating system. When we have multitask, there is something like multitask operating system. So with respect to the multitask operating system, we have some other thing, nucleus operating system is nu underscore something like that. Here obtain semaphore and release semaphore, take semaphore, release semaphore, post pend, obtain, release. Based on the semaphore there are different syntaxes. Based on the real-time operating system there are different syntaxes in this code. Semaphore makes the function reentrant. Reentrant functions are the functions which the real-time operating system's ISR and main routine can share the task, but shared data problem will not happen. For a reentrant function, the code should be atomic. That's very important, right? Multiple semaphore, as we discussed, multiple semaphores means there are different semaphores, and what are the advantages of multiple semaphores? That is what we have discussed. How does the RTAS know how the semaphore protects switch data? Semaphores as a signaling device, that is being discussed, and some examples are given. Semaphore problems, right? That's what we discussed. Forgetting to take the semaphore, forgetting to release the semaphore, taking the wrong semaphore, holding the semaphore for too long. This is what we have discussed, and this completes our chapter 6, which talks about semaphores is one of the major thing which prevents the shared data problem. And semaphore variants as discussed, right? Counting semaphores, reserve semaphores, and mutex semaphores are there. And ways to protect shared data. The one thing, disabling truth, this is what we did. The second one, taking the semaphores, and the third one, disabling the task. Switches in some way in between the two. It has no effect on the interroutines, but it stops the responses for another task. Good. Okay, so that is what the. And finally, chapter summary. The typical real-time operating systems is smaller and offers fewer services than the standard operating system. It is more closely linked to the application. So operating system is smaller, that's what it operating system is scalable, and offer fewer services than the standard operating system. Yes, for a simple ABS system, the Windows desktop kind of functionality is not necessary. Specific functionality is mandatory. This way it's smaller and offers fewer services than the standard operating system. It's more closely linked to the application, right? That's what it RTAS cannot protect itself. That's what we told. RTAS cannot protect itself. So RTAS are widely available for sale, and it is generally makes sense to buy one rather than write on yourself. Task is the main building block for a software written for an RTAS environment. Each task is always one of the 3 states: running, ready, and blocked state. The scheduler in the RTAS runs the PS priority ready task. Each task has its own stack. However, other data in the system is shared by all the tasks. Therefore, the shared data problem can reappear. The function that works properly, even if it is called by more than one task, is called as reentrant function. Semaphores can solve the shared data problem. Since only one task can take the semaphore at a time, semaphores can prevent the shared data problem causing bugs. Semaphore have 2 associated functions: take semaphore and release semaphore. Your task can use semaphores to signal one another. You can introduce any number of bugs with the semaphores. Priority inversion, deadline embrace are the 2 of the more dangerous. Forgetting to take or release semaphores or using the wrong one are the more common ways to cause yourself problems. The mutex and binary semaphores and counting semaphores are among the most common semaphore variants of the RTAS offer. 3 methods to protect shared data are disabling interrupts, taking semaphores, and disabling the task switches. Okay, so this is completes our 6th chapter, where tasks and data, tasks and task states, share data problem, how semaphores prevent share data problem, all are being refreshed. So the 6th chapter, which is Introduction to Real-Time Operating System, is being summarized and discussed in this presentation. Thank you.